I welcome you all to the lecture on the topic of finite difference method with Matlab programming. In this particular lecture, we will see how a second order equation is going to be solved with the help of Matlab programming, and we will take the example of a beam to obtain the solution. We will also compare the exact solution to this problem with the solution obtained with the help of finite difference method. We are taking the same examples which we have taken previously in some other lecture. There is a simple supported beam of length capital L. It has a point load W at a point C. The load is not at the center but is slightly shifted towards the left, and the beam is represented by a line AB. The governing equation to this problem is a second order differential equation which was already discussed in the lecture classes. In this governing equation, Y represents reflection, E is the elasticity, I is the area moment of inertia, and M happens to be the moment. As already discussed, this particular beam has a point load represented by W. This point load has to be manipulated to obtain the moments acting at different sections along the length of the beam. The boundary conditions required to solve this problem are going to be the known values of deflection, that is 0, at the two supports A and B. To obtain the identical solution, we start by finding the support reactions RA and RB. Then we find the moments for the two sections of the beam. The two sections of the beam are represented by AC and BC. In fact, both these sections have a different formula with the help of which the moment is going to be evaluated. So starting with the section AC first. For section AC, the bending moment is simply the reaction at point A, RA multiplied by X, which when substituted in the governing equation and integrated twice gives the cubic polynomial which is on display. It has two unknowns C and D which are going to be evaluated for the given boundary condition. In fact, at the moment only one of these unknowns can be evaluated. At x is equal to 0, the deflection y is 0, therefore d comes out to be 0, which gives us equation 1 as the deflection equation for section AC. Now coming to the second section BC, we carry out the same steps. We first of all find the bending moment and then substitute it in the required governing equation and integrate it twice to give equation number 2 having two unknowns E and F. Now out of these two unknowns, we can find the value of one unknown, that is F. To give equation number 3 as the required deflection equation for the entire beam, that is beam AB. Now in this particular expression, you can substitute various values of x to find the corresponding value of deflection, vertical deflection. for the beam, and that expression, that plot we have obtained, that plot we have drawn in the lecture classes also, so we need not repeat it over here. We will move forward with the numerical method, that is FDM. Now the basic steps of any FDM program are: we first of all initialize the problem, which is going to contain the initialization of the geometry, that is the length, cross-section area. Then the load is going to be given, material properties such as elasticity, Poisson ratio, all those material properties which are going to be required to find this solution are going to be specified at this stage. After this, we are going to form the stiffness and load matrix. In fact, the stiffness and load matrix are written by an expression kx into f, where x happens to be all the unknowns. In the case of a beam, the unknowns are going to be the lateral deflection of the beam, and if supposing the domain has been discretized, the beam has been discretized in 10 nodes. 10 nodes means in 9 parts. 9 parts are going to have 10 nodes. So if the beam has been discretized in 9 parts, the number of unknowns are going to be 10. So the X, that is the matrix containing the unknown, is going to be of size 1 column and 10 rows. Similarly, the matrix F, which contains all the loadings in terms of external forces or external moments, whatsoever may be the disturbing criteria, is also going to be of size equal to that of X. Therefore, it is going to be of size 1 column and 10 rows. And correspondingly, K, which is commonly known as the stiffness matrix, is going to be a square matrix of size 10 by 10. Kindly notice that in this particular formulation, or let's say in the formulation of any numerical method, the boundary conditions are substituted at the end. They are not going to be taken as they are not going to be considered in the starting, but the solution starts as if they are unknown parameters and are going to be substituted in these equations at the later stage. Therefore, when I say that the displacement, that the X matrix is of size 1 column and 10 rows, I am considering all 10 nodal displacements as unknowns. I am not taking the node at the value of displacement at node 1 and the node 10th as the known values. They are known because the beam is constrained at this particular end. Therefore, the displacement is known. That is, the value of displacement happens to be 0. But still, I am taking them as unknowns. This gives the size of the X matrix to be 1 column and 10 rows. Now, once the equation of this particular sort, that is an equation of the type which relates force to displacement, is known, then we substitute the given boundary conditions to these equations and solve them. Once they have been solved, I am going to get the value of displacement at the remaining 8 nodes. Kindly remember that there were 10 nodes in the starting, out of which displacement was already prescribed at the 2 nodes. So once the stiffness matrix is going to be solved, we are going to get the displacement values at the remaining 8 nodes. So once the solution has been achieved, we can plot them to have some graphical representation. Graphical representation is always easier to understand. Therefore, we are going to prefer plotting them instead of just drawing some tables or a text form of output. We are going to draw the graphs to display the output. So starting with the solution procedure, the governing equation is given by the second order differential equation, and since we are dealing with a beam of a same material and the geometry is also a constant quantity, therefore the term E and I can be taken out of the differential and can be transferred towards the right to give a modified form of the governing equation, that is del square y by del x square is equal to m divided by EI. Both E and I are going to be in the denominator. Now the support reactions are given by RA and RB, which are going to be used for finding the bending moment for section AC first and for section CB later on. Now these are the bending moments for section AC and CB obviously, but kindly notice that both these bending moments are function of X. They are that means that they are going to have different values at different locations of the beam, and these are supposed to be substituted in M, appearing on the right hand side of the required governing equation. The second order central difference approximation is given by this. We have already derived in the previous classes. So the first step to in the finite difference method is to discretize the domain itself. So we are assuming that we have a beam and it has been discretized into four equal sections. Therefore there are going to be 5 nodes in the domain: node 1, node 2, node 3, node 4 and node 5, and the value of displacements at these 5 nodes are going to be U1, U2, U3, U4 and U5. Kindly remember that since the beam happens to be constrained at the ends, the value of U1 and U5, both of them are going to be 0. Now the next step is the differential equation which is to be satisfied. Del square y by del x square is equal to m divided by EI, and when we apply this second order differential equation for a ith node, okay, we are applying this second order differential equation to a ith node where the value of I is going to vary from 2 to 3 and finally 4. We are going to apply the second order differential equation to 3 nodes: node number 2, node number 3 and node number 4. So when the differential equation is applied for the ith node, the equation what we get is ui plus 1 minus twice of ui plus u I minus 1 is equal to mi divided by ei and capital EI. If you compare this particular expression with the second order central difference approximation, the value of x naught, if the value of x naught is at the ith node, then x naught plus h is going to be I plus 1, and x naught minus h is going to be I minus 1. So this is how the expression is going to be written, and I is going to have 3 successive values. When I is going to be 2, when I is going to be 2, I plus 1 is going to be 3, and I minus 1 is going to be 1. Therefore, the 3 unknowns which are going to appear in this equation are going to be u3, u2 and u1. Okay, I am repeating this once again. When on the display now is the governing equation which has been discretized with the help of the central approximation for the second order. The equation has been discretized for the ith node. Therefore, we have terms appearing such as I plus 1, I and I minus 1 on the left, and there are terms of I on the right. Now, in this present slide, we are going to vary the value of I from 2 to 3 and then to 4. This is going to give us 3 equations for node number 2, node number 3 and node number 4. Kindly remember that the value of deformation for node number 1 and node number 5 are known quantities, and the discretization is applied for node 2, 3 and 4 only. So for the second node, when the value of I becomes 2, the equation becomes which can be simplified to similarly for the third node, the value of I is going to be 3, and the resulting equation is going to be and similarly for the fourth node, so on display now we have equation number 2, 3 and 4 which have been obtained as a result of finite difference method being applied to the discretized domain. Also note one more thing, that the application of FDM rules for node number 2 gives us equation number 2, and application of FDM rules to node number 3 gives us equation number 3, and application of FDM rules to node number 4 gives us equation number 4. That means that whatsoever might be the number of the node, whether it is 2, 3, 4 and so on, the equation which we are going to get is going to be that particular same in number. For example, if the domain has been discretized into, let's say, 100 nodes, then the FDM equation for node number 2 is going to be second equation. FDM discretization for node number, let's say, 40 is going to be the 40th equation, and so on. And obviously all these equations are going to be arranged in a matrix form, so we need to know where all equations are going to be arranged. So these are the 3 equations. The other 2 equations are the constraints equation for node number 1 and node number 5. Arranging all the 5 equations together, we get these 5 equations arranged together. The value of u1 is 0. The value of u5 is also 0. This is because the ends of the beam are constrained, because they are simply supported, and the unknowns are u2, u3 and u4. These 5 equations can obviously be arranged in a matrix form. So what we get is the equation in the matrix representation. Now all the terms appearing on the right hand side, obviously they are known, and the value of u1 and u5 is also known, but this equation can be solved, these equations can be solved to get the value of u2, u3 and u4. Now the thing to be noticed is, though the equations have been derived for constant m, e and I, we can easily substitute any value of m, e and I to simulate the case of a variable cross-section area, elasticity and moment. So kindly notice that though we have started with a relatively simple case of a constant cross-section area case with one material, with a rather simple loading on the beam, the thing is that we can very well substitute the value of bending moment, elasticity and cross-section area, which is given as m2, m3, m4 for bending moment, e2, e3 and e4 for elasticity, and I2, I3 and I4 for the area moment of inertia. All these values can very well be taken for a variable case, and the corresponding FDM formulation of a more realistic case can be obtained. The first line of the program starts with a comment, that is the percentage sign. This comment is used to give something as a explanation, such as one dimension deflection, which is the name of the program itself. The first line which I write in the program is a clear command, which is going to wipe off the workspace which might contain any variable from the previous session of the Matlab. The clear command is going to clear the workspace of all the variables. The next command, CLC, is going to clear the display itself. Now this is the elasticity represented by E, area moment of inertia represented by I. DIVI is equal to 20. DIVI represents the number of divisions in the domain. The current value of number of divisions happens to be 20. That is just for the initialization. Length happens to be 1 meter, that is. W is the point load. The current value of point load happens to be 2. N into ES, that is the number of nodes, obviously is going to be number of divisions plus 1. So if division happens to be 20, number of nodes is going to be 21. This line gives you the length of each division, that is L divided by divi, which is going to be stored in H, because H is the symbol which we have used in the FDM formulation in the theoretical development. So we are using the same symbol H. Now this line, that is x is equal to 0 semicolon dx semicolon L, is going to generate a matrix. The first value of the matrix is going to be 0. The next value is going to be 0 plus dx. The third value is going to be 0 plus twice dx. The next is going to be 0 plus 3 times dx, and so on, till we get the last value of L. For the current case, when the value of L happens to be 1 and dx is 0.05, because L is 1 and divi happens to be 20, the value of dx is going to be 0.05. Therefore, the X matrix is going to contain values such as 0, 0.05, 0.1, 0.15, and so on, till we reach the last value as L, which is going to make that the matrix X contain 21 values corresponding to the 21 locations of the nodes. The line on display, DEFL underscore point underscore load, this is the name of a function. The particular arguments which are being passed to these functions are x, e, I, w, and L. X obviously is a matrix containing the 21 locations of the nodes. E is the velocity, I is the area moment of inertia, W is the load, and L happens to be the length of the beam. So when these 5 parameters are passed to this function, it computes 2 things which are being stored in M and DEFL underscore ACT. M in fact is the moment at 21 locations, the same locations as which are stored in the matrix X, and the DEFL underscore ACT is again a matrix which is the actual displacement of the beam at the 21 locations. By actual displacement, I mean this particular function calculates the exact displacement, because the formula is known, it has been evaluated in some of the books. The particular book which I have referred for this example is the Strength of Materials by Dr. S.S. Ratan. So persons who are interested in finding the theoretical perspective of this particular problem can have a look at the book to find the formula which is being used and how it is being derived. But for the time being, the values of x, e, I, w, and L are going to be passed to this particular function, and the output of the function is going to be stored in M and DEFL underscore ACT, which are the moments and the actual value of displacement at the 21 nodal locations. Coming to the next line of the program, EI is equal to E multiplied by I into ones 1 comma NNO DES. Now the meaning of E and I is clear. These are elasticity and area moment of inertia, of course. Now this function named ones, ONES, and the arguments 1 and nodes is going to generate a row matrix. The size of the row matrix is going to be one row, and the number of columns are going to be equal to the value stored in the variable nodes NNODES. Because the value of NNODES is 21 presently, this particular command once generates a row matrix containing 21 columns, and the value at these 21 places is going to be 1 at all 21 places. So this particular command generates a row matrix containing 21 columns with value 1 is stored at all those 21 places. And when this is multiplied by E and I, the output which is going to be stored in the variable EI is going to be EI at all those 21. E multiplied by I is stored at all those 21 places. So just as an example, if the value of E happens to be 2 and the value of I happens to be 0.1, so EI is going to be 2 into 0.1, that is 0.2, and 0.2 is going to be stored in all 21 places of the matrix. So this is how this particular line is going to work. Now this command k is equal to zeros and within bracket nodes is going to generate a square matrix of size nodes into nodes, because nodes has a value 21. So this matrix is going to generate a square matrix of size 21 into 21, and it is going to be all zeros everywhere. And this matrix is going to be stored in a variable known as k. K is a standard variable which I use for the stiffness matrix. Now after this, I am generating a force matrix represented by capital F. In fact, the function which is being used for generating the force matrix is the same as has been used for generating the stiffness matrix, but in this case the arguments which are passed to generate the force matrix F are nodes, 1, but the name of the function itself is zeros itself. This is going to generate a single column containing 21 rows, and at all those locations there are going to be 21 zeros. So kindly note that in Matlab, a command can be used in more than one way. It depends upon the number of arguments which are given to it, and it also depends on the number of outputs which are going to be at the receiving end. In this particular case, when there is only one input, it creates a square matrix, and when there are two inputs, it creates a 2D matrix corresponding to the number of rows and number of columns which are specified. In fact, when there are 3 inputs to this function named as zeros, it is going to generate a 3D matrix, and if there are 4, it is going to generate a 4-dimensional matrix, and so on. Now coming to the actual generation of the finite difference method equations, this utilizes a recurring relationship which is going to be embedded within a for loop. The for loop is going to start from 2 and is going to end at nodes minus 1, and this particular value is going to be stored in a variable named as I. The rest of the program is going to explain itself, that is on its own. So I'm not going to do the explanation part of it, but I am going to simply display the lines of the program one by one. The students are required to understand it, they are required to write it down, they are required to run it step by step, so that they can get the experience of the programming. So here we go.
Okay.
Now in the next slides, we will see the results obtained after running the program in a graphical form. Matlab has a very strong, it is very strong in plotting graphs and graphs of various types. So as the results have been obtained, some lines have also been done in the program itself to plot the results so that the user can view it. This is a very strong feature in the favor of using Matlab. Now the students are required to see the results closely. They are supposed to interpret the results in a logical manner, and they are requested to inform if any discrepancy occurs. Now this is one of the graphs. It has length on the x-axis, it has moment on the y-axis. Obviously the case which is being analyzed is a point load. The load itself is not exactly at the center. It is somewhat towards the left, and for this particular point load, the bending moment diagram is going to have a triangular shape. So this is what has been evaluated by the program. Now this is length versus actual deflection of the beam. Now this is we have two plots over here, one in the blue and one in the red. One of the plots represents the actual deformation of the beam obtained using the exact analysis, and the other one represents the solution obtained using the finite difference. And as can be seen, that for the discretization using 21 nodes, that is 20 parts, the solution given by the exact analysis and the solution given by the finite difference analysis, they happen to be almost identical. Now this plot shows the difference in the deflections along the length, and as you can very well see that the difference has been plotted along the y-axis. And have a look at the scale also. The maximum difference is 2 into 10 raised to power minus 8 meters at a location of x is equal to 0.4, which is almost a negligible difference. But obviously the difference can be further decreased, or you can say that the quality of the solution can be further increased by dividing the domain into a larger number of parts, or you can say that by working with a still larger number of nodes. This is obviously one of the features of any numerical methods. The numerical method is going to give you a solution which is going to converge, or which is going to approach the exact solution as the number of nodes, or you can say that as the discretization becomes more finer and finer. Now this is going to be guaranteed only if there are no errors in discretization, there are no errors in programming itself. So if you are obeying all rules, taking care of all theoretical and practical aspects, only then the solution given by the numerical method is going to approach towards the exact solution. Now on display now is a function which is going to give you the bending moment and the actual deflection for the case of a uniformly distributed load. The previous function was for a point load, but this particular routine has been developed to give you the value of bending moment and the actual deflection for a uniformly distributed load. this is the corresponding length versus moment diagram. It is symmetrical as is expected. It is symmetrical with respect to the central axis. This is the deflection curve, that is the actual solution, exact solution. And in this case we have the exact solution and the FDM solutions in the same plot. As you can see that both the solutions are overlapping, so obviously the accuracy of the solution obtained through a finite difference method is pretty good, as has been illustrated in this particular diagram. And this is the plot for the difference in deflections. The maximum difference is somewhere around 5 into 10 raised to power minus 9 at the somewhere at the center of the beam.